Okay, let me start recording. Okay, now today we're going to look at Bernoulli equation. We're going to derive the equation from conservation of mass and also momentum equation. All right, so if you look at the diagram on your screen, we have a stream of fluid that flow from the left to right, and then the axis given at the bottom of the corner there. You see that our x-axis is to this direction, y is to this direction, z in this direction, and then our gravitational force is acting in z direction. Okay, so this will help us to define our location and direction also. So since our fluid is flowing from the left to right, we are using a cross section. In this case, we use a cylindrical cross section from the left to right. You see there's a cross section over here, and we have all the parameters like usual when we study about fluid. We have pressure, we have density, we have Vs is the velocity of our streamline, velocity of our streamline here, velocity, and our area of our cross section here. Then there will be we draw a control volume here. We draw a control volume like what we did for our momentum equation. So after a certain distance or a short distance, we in this diagram we see it as a ds, a very short distance ds. So after ds, we see what happened in another cross section area here. So we see that the pressure is increasing, not increasing. There is a changes of pressure. So we write pressure P plus dP at this cross section, and then the rho in this case do not change. All right, do not change because this is the limitation of Bernoulli equation. So when we derive Bernoulli equation, we have to take note that density inside the system or inside our control volume do not change. Okay, so this is the main key point when we derive Bernoulli equation. So next time when you use Bernoulli equation also, take note that the density should not change over a certain distance. So in this case, you see that if you compare from the lower area and the upper area here, the density doesn't change. And then the velocity, there's a change there. So we write V plus dVs. There's a change of velocity there. And then the area also changing a little bit. A plus dA. dA is a small changes. So we're going to use differential equation to derive the Bernoulli equation. Okay. In this case, we had a body force that our fluid interact with the control volume, and there's an angle of theta over here, which is how to measure this theta is that you measure from the direction of the streamline at the center of your control volume, the axis, or we call it axial axis. So we measure from this location to the y-axis over here, right? So we have a theta over here, right? So this is how we start by understanding the diagram first. So all the lines that you see here is a streamline. It's the direction of your fluid here. So how we start? So we're going to use conservation of mass equation and the momentum equation to derive the Bernoulli equation. Because we are studying about the fluid dynamics or fluid mechanics. So Bernoulli equation is very important for this module. Okay. The next line that you see on the screen here is all the keyword also. We will look at the steady flow, incompressible case, and we assume there's no friction inside the flow. All right, so we have a steady flow, we have incompressible. So when you're not able to compress the medium or element, your density always stay the same. right? Compressible, if you see the word compressible, it means that something linked with the density. Then frictionless flow is important because if there's a friction there, then there's a loss of energy. Then when you have a loss of energy, there is an error or there's a constant value that you need to put inside the equation later on. So in this case, we don't want to make the equation complicated. We assume that it's a fluxless flow. So when you come to your lab report, when you when you get the data and then when you do the calculation later on, the value that you seen in the experiment might be a little bit different from a theoretical analysis. So for example, I give you the area from the machine, the area, the velocity, the pressure from the machine itself. But when you calculate for the parameter, the value sometimes will have plus minus a value there. So is because that we have all these assumptions inside inside the equation. So when you write report, when you see something different from the value, or you need to write the error that inside your experiment, then this is one of the point. You can write that. We assume for the Bernoulli equation, we assume that our apparatus do not have friction inside the flow. And also we assume it's incompressible and we have a steady flow. So we have to write all this error inside the report. Okay. So again, we start with steady flow, incompressible, and frictionless condition. And we use the control volume as what you see on the screen here. The dashed line over here is our control volume. Yeah. And all this control volume is going along the streamline here, right? The streamline. And the S here is a length between your inlet and outlet here, right? Inlet and outlet here. So we have a ds here. What else? Okay. So there's a reason why we choose the differential control volume like this. It is because we want to study that the flow across the bounding surface only happen at this at this section, yeah, at the end section, which is here, yeah. So our control volume is following the streamline, yeah. If your control volume do not follow the streamline, means there's your body force here will be different, yeah. So there's a reason in our derivation here, our control volume is parallel to the streamline or bound by the streamline. Okay, so to start derivation, we have to know the location of our reference point. The first point that we look here is that I label for you with the red dashed line here. I label as S. So S is our starting point. And after a certain distance of different distance, at location number 2, we have S plus ds, with this location at this point. And S plus ds stand for the location, and all these parameter will be used for derivation. Okay. The next one will be, we assume all the parameter is positive value, where pressure increase, velocity increase, area increase. Okay. So these are the assumption when we derive. So the first is a property of the fluid itself. We have a steady, incompressible, and frictionless flow. The second one is the all the parameter here is increased with positive value. Right. Okay. We start applying the first equation, continuity equation. So continuity equation give us by this. I think this one you already familiar. So What is continuity equation? Is basically your m dot, the mass flow rate. So continuity is about mass, the change of mass. So when you take rho times volume, you get mass, divided by T, you get m dot. So same with the control surface dimension over here. You take rho times velocity times area, you get mass flow rate also. Only you need to know that from continuity equation, we look at what happened in the control volume plus what happened in the control surface. Again, we need to call back the assumption. We have a steady flow. There's no flow across the bonding streamline here. So it means that the flow, there's no flow go outside this one. All the flow is flowing the streamline. Okay. And we have an incompressible flow in this case. So when you have an incompressible, the density will be constant inside the equation over here. So because we have steady flow, you can always cancel the first term here. And then you write steady equal to 0. Again, for exam or for your assignment, when you need to use the equation, you write the equation, and then you do the assumption. After that, you do some notation on the equation itself. You write an arrow and then write steady equals 0. You'll get some marks for all these notation. Yeah, at least 1 mark for equation, 1 mark for arrow and the small notation of this one. This combination will give you at least 2 marks over here. Right? So the next one, you look at what happened in the control surface. So I think when you look at this equation, you know how we get this equation already from the vector form. Yeah, v dot dA, you look at this section. Area always positive, which is pointing to the left in this case. And then you times the vector direction, you get negative. If you look at this direction, you will get positive because area always pointing to outside. In this case, it's pointing to the right. And then the velocity is going to the right. So your combination of v dot dA in this section will get positive. Yeah. So if it's still not clear, you go back to the previous lecture video and listen to it or watch it. So I skipped the equation for derivation of this control surface term here. So straight away I write the answer for you. So as you can see here on the screen, this equation consists of two terms here. One is on the left hand side, which is this area. This one represents what happened in this area. Okay, now how do you get this one? So rho, you copy the rho. V dot dA, you sure get negative there. Yeah, you will get negative. Okay. All of you understand, right? Do you need me to explain again why this one, the dot product, get negative?
No, sir. Okay.
Good, everyone good, Cool, you good,
Yes.
Okay. All right. Then the second one, why this one got plus? Because you are looking at this section. So you just consider what is happening to the velocity. So you get v plus dvs, and then the area also increase. So a plus dA. So actually this one is the rho VA, which is this one. So you get positive here. And after that, you just rearrange. Okay, so this is just a mark for you lah. So the first term is for the location over here. Second one is over here. Okay. The next one will be, okay, the next one is just expansion of the equation, and then we simplify the equation. So when you multiply the products inside there, so you multiply rho VS, rho plus rho dVS, and then multiply rho into A into this one, then you simplify the equation, you'll get this equation. So inside the equation, you'll see all the rho around, you factor out, you take out the rho. At the end, you only see V times dA plus A dVS plus dA VS equals 0. Okay, so there is some calculation between the first line and the second line, like what you see on the screen here. I also didn't do the didn't show the step for you. As your homework, you try to expand this equation. You times the row inside there. Yeah, this is the quadratic equation. You times inside, then you get the term, then you simplify equation. At the end, you get this one. Okay, so mathematic model, when you see dA, D is a differential, means small changes. Then you times two small changes term together, you get roughly you get almost near to zero lah. Because small changes plus small changes, you'll get very, very small changes. Okay, you imagine that dA maybe is 0.01, dV is maybe 0.01, you times 0. These two you get 0.000001, very small. So if you have a product of these the two differential, we can ignore this one because it's very small numbers compared to these two. Yeah. So of course, when you do your lab report or when you do analysis later on, the value will be more or will be less because of this simplification in the equation development. When you derive the equation, we have the assumption, number one. Number two is because of the products of differentiation. So in this case, we take out this one. So we get we focus on more bigger number. Okay. So straight away you use VdA plus A dVds equals 0. So this equation is from the continuity equation. Okay. So remember this term, and then later we need to substitute this one into the momentum equation. Then from there we will get the Bernoulli equation. So at this moment, I think no complicated formula over here. Maybe what is confusing is the plus dVds over here. So this one you refer to the diagram, and then the rest is just normal mathematical steps. Okay, so yeah, so this one is here. Okay, now we are complete with the continuity equation already. So continuity equation, you get this equation. Then the next one we look at momentum equation. So momentum equation, as what you see over here, we will, I think you're familiar also. So momentum equation is mv. Maybe I help you to refresh a little bit. Momentum equal to m mass times velocity. So you know that you derive second Newton law, F equal to ma. Again, A is a V divided by T. You get the products of M times V divided by T. It actually is a momentum divided by T. So when you want to get the forces in the system, you take the momentum divided by T, you get force. That's why this is the basic of the derivation for momentum equation. However, in this case, we are focusing on the certain direction, which is along the streamline. So along the S direction, along the streamline. So on the left-hand side, we have forces, body force plus surface force. On the right-hand side, again, we are seeing the control volume term and control surface term. So we have volume times the rho v plus velocity times the rho v dot dA. Okay. Again, if you're not sure about momentum equation, go back to the previous slides for the momentum equation content. So again, bring back the assumption so that we can simplify the momentum above. So number one, steady flow. Second one, there's no flow crossing the control volume or control surface here. And we are having a incompressible flow where our rho will be constant and no friction, no friction in the system, so that our surface force later on will be focusing on pressure only. Yeah, we'll focus on pressure only. There's no pressure force. So the first one, because steady flow, we cancel the first one. We cancel the control volume term, draw an arrow and write steady equals 0. You get some points for that. Then we look at what happened to the surface force due to pressure only. So I give you the whole equation that derived from the diagram over here. So for the surface force in the S direction, so you see S sub S means surface force in S direction only. So equal to, you look at the left hand side, because it's due to pressure. So you how you convert pressure into force, you take pressure times area. So you're looking at the S area over here, you take pressure times the area over here, you get the pressure at this side. And then you consider this side also. You take the pressure in this side on the second area over here is P plus dP. There's a positive change of pressure over here times the change of area over here, so A plus dA. And then the third term here, is P plus dP over 2 dA. So this is you can say at the center of the stream here, right? So I make some marking over there. So this one is previously what we looked when we consider momentum equation. So P, the first term and the second term here, we will have pressure force on the end face of the control surface. What you need to focus on the screen here is you have a negative sign here. Why you have a negative sign here? Because the pressure always acting to the surface, yeah. The pressure always acting on the surface. So pressure, you go to this way, you get positive. While at the second area over here, at the location of S plus ds, this location, the pressure is acting opposite or against the S direction. So you get a negative sign there. Okay. Then what happened to the third term on the screen here? Like what you see on the screen, there is a notation there. So this term is your pressure force acting in the x direction on the bounding stream surface, which is on here, on the body over here. All right, over here. So if you draw only the skin of the control volume is this one, only the skin, and the pressure is acting on all this screen. So this is the we write as FSP. Yeah? FSP is due to the bounding stream surface, which is over here. Yeah? So it's a little bit different from what we've seen in the previous slides for momentum and continuity equation, because now we are trying to derive the Bernoulli equation. Okay, so again, so the first two term is pressure force at both ends. Now we have one more force that exists at the bounding surface here, right? Because previously we are consider a pipe, we consider a moving body through a channel and all this, so we don't have this component. But however, today we look at something happen within the streamline. So within the streamline, so we have something that bound the control volume. So we will consider this term here. Okay, P plus dP divided by 2 dA. So if you multiply the products for this equation, you multiply and then you simplify the equation, you will get negative A dP minus half dP dA. So again, in this second line of equation, you see there's two differentiation equation, very small changes of pressure times very small changes of area. These two will be a very, very small number that you can ignore, right? You can ignore compared to this term, because the value is significantly different. Right? Okay. So after that, we write the momentum equation again. Previously, we looked at surface force, yeah? All the slides before this is surface force. Now we look at body force. Body force always linked with gravitational force, which is your mg. So how do you get your mass? You take the rho times the volume. Yeah. No, rho times the not rho times volume. Mg. So in this case, we use the momentum concept. We take the rho g times the velocity. Okay, times the velocity. Sorry, not velocity. This is volume. This is volume. Okay, we take rho g times the volume because body force is mg. So to get mass, we take rho times volume. Okay, apologize for the wrong notation. So this is a volume. Yeah? So when you derive the volume, we take area times the ds, we get volume. Yeah? So A plus dA is a differential difference in the system times the ds over here, we get our volume. Okay. So again, this is volume. And then when we look at a certain direction, which is along the stream direction, we convert according to this angle. So we convert the gravitational to the stream direction, yeah, to the stream direction. So you have a angle over here. So your G is actually a sine, yeah. If you draw the vector diagram, this is your G, this is your theta. So this is your stream direction. So between the opposite and hypotenuse is sine. So you get negative G sine theta. So why you have a negative there? Because your gravitational is moving down. Your axis is always pointing up positive. So that's why we have a notation of negative here. So the next one will be if you times, you expand the equation here. Your dz is for mathematical model from the diagram itself is sine theta ds, which is if you expand, this is your ds, and then this is your theta, and then you look at the axis itself. This is your z-axis. So if you get the relationship between dz and your ds is a sine relationship. So this is mathematical model that derived using the angle over here. Yeah. Then you change the ds term into dz term. Okay. Because it is very difficult in the reality in the real life to actually monitor the ds, but you can monitor the dz in the real life, right? The vertical direction you can monitor, right, by the way you orientate your pipe, you orientate your tube and all this. So your dz you can orientate, but you cannot properly monitor what's happening to your ds component. So you convert, there's a reason why you convert your ds term into dz. Okay, so after that, you continue. we look at momentum flux, which is from the momentum equation itself. So this one, the V rho V dot dA is your momentum flux actually. So you rewrite, you change the V terms according to the scenario we have here. So in this case, we are using your US, right? You just change the notation, US rho V dot dA. And then this one, if you do the conversion, you will get two term again. This one you convert, so you know how we get the V dV already. So area vector always pointing out, and for section 1 or inlet just now, the velocity going this way. So you get a negative sign over here for this term. And then at the exit there, area always pointing out, velocity going out at section 2 outline there. So at outline there, you know that there's a change of velocity. This is your velocity. This is your rho. This is your volume. And then this is your area. Yeah. So there's a change of a velocity there. So again, this one is from the momentum flux. Yeah. So we have rho. We have the velocity. V rho V dot dA, so we have 2 times of velocity there. So that's why in the second term or the first term here, you see there's a 2 velocity there. Okay, you see 2 velocity, it means that you are looking at momentum equation. Okay, this area. Okay, and for the second term, you should understand why there is no negative there, because the dot products of vector is positive, and then negative because of the dot products of the vector is negative. The next one will be all this you can read from the screen. So we will have this equation. You can rearrange, yeah. You can rearrange the products of all this into this form. Okay, this one, all this you can rewrite in this form, yeah. So after this, you just continue to derive, yeah. So you see this one, rho V S plus dV times the A plus dA, this whole thing will be equal to rho V SA. And then the integration, this term, will be equal to this one plus this one, because you already replace this term with this one. Yeah. The way we write this equation is based on the explanation that you see on the screen here. Yeah, is because of the continuity concept. Yeah, it's based on the continuity concept that we already can prove that this one equal to this one. So we simplify this term as this one. Then you simplify the mathematical model over here. You times and then you simplify, you arrive at this term here. So integration of the momentum flux in the control surface will equal to rho VA dVs. Okay. Then you go back to the equation. You substitute what we derived just now. You have your FSS, you have your BS, you have your integration of U rho V dot dA. You assembly all these three together into this equation. Okay, it's a very lengthy equation, but it's just an assembly of what we derived just now. Okay, so this one is FSS. This one, Okay, this one and this one is your FES, and this one is the integration CS. Okay. Then you divide your density and area. You divide your density and area in this equation. And again, if you have a dA times dz, the differential terms you ignore in the steps, and you arrive at this equation. Negative dP over rho minus G dz equal to Vs dV. Yeah. Again, V here is a volume. Yeah, it's a volume. It's not velocity. Yeah, it's a volume. Equal to dV s squared divided by 2. This term is, you can write as dV squared divided by 2. This is from mathematics. Yeah. And then you arrive at the familiar form of Bernoulli equation that you've seen in physics class. You have dP over rho plus dV squared divided by 2 plus G dz equals 0. So again, this term is called the basic form of the Bernoulli equation. So this is a basic form of Bernoulli equation, and then we will look at what happened when we have an incompressible scenario. So when you have an incompressible scenario, you can integrate the equation from one point to another point. You can take out the differentiation inside the equation over here, which is dP, the small changes of pressure, the small changes of velocity, the small changes of the elevation. You integrate, you'll get the full value of pressure, velocity, and your elevation equal to a constant value. This one is the Bernoulli equation. However, the Bernoulli equation, it must meet these 4 criteria if you want to use this equation. Yeah. So the question, when it comes to your exam question, you must look carefully. If the question have mentioned steady flow, have mentioned no friction, have mentioned incompressible flow, and sometimes as an extra line, it will help you. It will say that the flow is along the streamline, or find the pressure along the streamline. Then if these 4 criteria is met, then you can use the equation in the bracket, in the red bracket that you see on the screen here. Okay, so today we look at Bernoulli equation, how we derive this one from the continuity equation and also from the momentum equation. Then for the next class, we'll look at example, some tutorial question, and then you are ready for your test 1 already. Okay, yeah. Let me stop the recording.